Hi, in this video, we want to take a look at the nlme's implementation of generalized least squares. Okay, so we're in the situation where we're doing linear regression. Now, remember that linear regression, we have some assumptions. First assumption is that we have that linear model. Okay. Expected value of the residuals is equal to 0. So the expected value of the residuals given x is equal to 0. We have constant variance. All right, so when I say constant variance, that means that the variance of the residuals given the predictors is the same regardless of what the predictor variables are. And then last but not least, we have covariance equal to 0 between residuals. Okay, so what if we don't have that? What if we're in a situation where that's just not the case? We look at our data, we look at our model, and we conclude, hey, one of these assumptions are violated. All right, well, so here we're going to focus on constant variance and covariance of 0. Okay, so if I don't have constant variance, some options I have up until now is to do a linear model where I use a transform, or I can adjust the weights, or I could do both. And that's been presented before. But maybe it's a little bit trickier. Maybe it's a more complicated situation than that. In that case, we want to get a little bit more powerful of a situation going, and so we'll go ahead and use a generalized least squares model. In that case, we'll use the bar power function. Now, if we do not have 0 covariance between observations, then what we're going to have to do is something a little bit more exotic, more interesting, and the generalized least squares model handles a wide variety of, maybe not wide variety, a variety of the situations that we can find ourselves in. So let's go ahead and take a look at this package. All right, so this package is probably the most common implementation of generalized least squares in R. So I decided that we're going to go over it. This video is going to be just going over functions in this package. Now, when to use what, why to use it, other details are not going to be covered here. Here, this is just so that it gets on your radar, like, hey, I know that I have these options, and you can go and look at the help documentation and look at textbooks to see what is the best course of action. This video is going to talk about time series topics very quickly without explaining what's going on with them. And if you need to get, if you're not familiar with time series, go ahead and get a time series book. A time series course is a course in and of itself, so this video is not going to be able to do it justice. All right, so for this video, I'm going to load the nlme package. Now, those of you who have been watching my videos for a while know that I almost always use the double colon notation. I do package, double colon, then the function that I want. Here, everything is all about this package, so I'm just going to go with this package straight out. And I try to avoid loading packages because of the issues with package confusion. Python handles this aspect of data science much better than R. All right, so something that needs more attention in the R community is if I say citation and then in parentheses the package I'm interested in, I'll get citation information for this. So one thing that's nice about this for us college students is that what I can do, if I do anything with R whatsoever, I can use citation to get easy, quick and simple citations for my work. And so if I was to do a project, I make a histogram or I make a bar plot or something like that, I use R, I can use citation, and boom, I get an easy citation to get my citation count up to convince people that I'm actually doing good work. And if you are a LaTeX user, here's the BibTeX citation information for you if you're interested. And here is where you can actually get the actual information for the package. All right, so what this package does if I want to build a model, I go through and I build it and I declare some features of it. Or if I'm going to do something that requires the residuals to be computed, what I have to do, I have to build like a baseline model and then use the update function to build the model that I actually want. So here, these are going to be like our baseline functions. What we're going to do with these functions is I'm going to look, I'm going to go, hey, I don't think the residuals have zero covariance. And so I'm going to do something like maybe autoregression, something like that. Well, if I want to fit an autoregressive model on the residuals, I need the residuals to do that. So what we have to do, we have to have the model first, and then we pass this into the update function to get the specialized format for us to fit on our residuals. And so what I'm doing here, I'm just taking examples from the nlme package, and I'm just taking a bunch of examples from the help documentation, and all of the examples use data sets that are loaded inside the package. So by loading nlme, automatically I have this data for free. I don't have to load it. I don't have to do, read.table, read.csv. I don't have to do any of that junk. Okay, so let's say I believe that I have non-constant variance, and I want to use different weights to adjust for this. Well, so remember, when I say constant variance, that's constant variance with respect to x. So if x changes, the variance of the residuals does not. All right, so what you do, you take the function, the generalized least squares object that you already built. So this is my generalized least squares fit. And then I pass that to the update function, and I say that the weights are equal to var power. All right, so what this will do is this will make an adjustment for me automatically. So it takes the residuals from here, it takes the fit from there, it takes the formula from there, and then it changes things so that the weight of each observation relates to the residuals, so that I can get a better fitting model. Okay, so I can also, if I believe that my residuals are depending on pressure, then what I can do, I can use the form. I can say tilde, it's a one-sided formula, tilde pressure, which is a predictor variable in this data set, and then this will make an adjustment for me. So here, I'm not specifying a formula. Here I am. All right, next, let's consider autocorrelation. All right, so let's say I build a model and I look at my residuals and I think, hey, it's kind of like a roller coaster plot. It looks kind of like, it looks like whatever the previous residual was, that's close to what the current residual is. So as I move along, if I see that, if I look at a residual, the next one is somewhat close to it. And then when I look at the next one, it's somewhat close to the previous, somewhat close to the previous. If I see that kind of trend in my residuals, I might want to consider autocorrelation. So here it's autoregressive of lag 1. Now on this one, what I have to do, so object created using the constructor must later be initialized using the appropriate initialize method. What this is saying, I have to build the model. So I go, sorry, I build the model and pass the data, and I have to say correlation, I have to pass a formula. And here I'm saying it's constant given the MARE column. So here in this package, just like pretty standard throughout R, the vertical line is given. Now something I can do, I can take the autoregressive model that I just built, and I can go ahead and I can update it to have weights determined by the var power function. And so what the update function does for me in this, I can go through and I can keep on updating the model. So I build my model, I take a look, I say, hey, this is my #1 concern, I fix that. Then I look at that model, I go, hey, I want to adjust that further. I can keep on going. So here, in this model, so remember we built the baseline model, then we got auto regression of 1, and then for this one, we adjusted the weights to get constant variance. Now here, it's very similar that we took a generalized least squares model, then we changed the weights based off of variance, then we added an autoregressive aspect to the correlation between residuals. So I can keep on building on it to get what I want. Now, when it comes to the correlation aspect, you have quite a few options in this package. So for example, we can do general correlation structure. And for this one, the key aspect is that correlation is equal to core sim. And I can pass a formula on the inside. So I'm saying one-side formula given subject. So given the subject predictor variable, it's going to be constant given the subject. Now here at the same time, I'm adjusting the weights. I'm saying the weights are constant given the age variable. We can also have compound symmetry correlation. So here on this one, I'm doing update. I'm taking this generalized least squares model, and then I'm going the compound symmetry correlation structure, and I'm passing this formula to it. We can also have rational quadratic correlation structure. Now on this one, once again, I'm using the update function. I'm taking the original generalized least squares. After looking at the residuals, I believe that there's a correlation between the residuals. So I want correlation rational. And here are my parameters. And I'm passing a formula to it. So I'm saying that residuals depend on latitude and longitude. And nugget is a parameter. For nugget, the default state is false. And here I chose to do true. It'll take a little bit longer to fit if you put nugget equals true. Next, we have spherical correlation structure. And this is very similar to the previous. It's just the main difference. Here I have rational, and here I have spherical. Otherwise, it's pretty much the same. All right, now, once I have my model, I want to go ahead and start doing some diagnostic plots to make sure I understand what's going on. All right, so part of a generalized least squares model is that it groups the data together. And these groups are looking for correlation groups, basically. All right, so when I plot, let's say I'm going to take the ovary correlation autoregressive 1 model, where I'm going to say that the residuals of type P depend on the fitted values. Now with this dot, I'm just saying, just grab the residuals, grab the fitted values, all of them. And here we're going conditional on MARE, and I want to plot it. Okay, so this is the formula. I'm applying the residuals of type P. So remember, I have 3 types of residuals. So I've got Pearson, response, and standardized. And so I'm saying residual will be vertical axis, x-axis will be the fitted value, and AB line equals to 0 means I'm slapping a horizontal line that the average should be approximately balanced around. all right, well, I can do the same thing, but if I change AB line to 0, 1, then I'm going to have 0 for the y-intercept and a slope of 1. So this is the line y equals x. So here we have follicles being plotted by fitted. So if I have a perfect model, these should form a straight line. And also, if I just plot straight out without the additional information, it'll give me box plots, and it'll do it by the groups. So each of these is a different group formed by, or approximated by, the modeling structure. Okay, well, something I'm going to want to do if I'm dealing with autocorrelation, I want an autocorrelation plot, and I want to be able to grab the autocorrelation function. So here, if I go ACF, it'll give me the lag and then the correlation between observations and that lag of observations. All right, so we can see that it decreases down. It bounces a little bit here, but generally decreasing. And it's hard to interpret all these numbers, so let's go ahead and do the feather plot. And I can see it decrease. Now, if I'm interested in a specific structure, like given a predictor variable, I need to use this. If I use the regular ACF function to plot, I don't have as much flexibility in this regard. And I went ahead and I applied the regular ACF function. Now here, this is not going to be able to pick up this formula. All right, so here, this output is giving me, it's taking the residuals given the subject information, and that's where I get these values. When I do this version, you'll notice that I don't have that conditional formula in there. Well, look what happens when I take a look. All right, this autocorrelation is 0.77. When I look down here, you can see that's just a little bit better, a little bit bigger than 0.6. All right, so these are two different measurements. So regular ACF is great, but I don't have, if I want to eliminate the influence of some variables, I don't have that ability. That's one thing that's nice about this package. All right, so just like we always do in linear regression, I want to look at the normal plot to see if my residuals are normally distributed, because if they are, then I get a whole bunch of things for free in terms of hypothesis testing. And for this particular example, yeah, that's pretty close. I mean, it's kind of troubling that everything here is lower, but it's pretty close. It's probably an asymmetric distribution, but it's nearly Bell, so I would be okay with it. Now we can get the semi-variograms. So what we do, we just pass the function. We give the conditional formula. So it depends on time and rate. Here's the output. And we can go ahead and plot it. And here we can see that the semi-variogram increases as distance increases. All right, just like in the rest of R, we can summarize the general least squares object. So something that's nice about this is that it gives us AIC, BIC, and log likelihood. It tells us, the formula. It tells us, what was our correlation structure. Gives us a parameter estimate. It gives us our confidence intervals, or sorry, no, this one's hypothesis. This one gives me hypothesis testing on these. gives me the correlation between predictors, residuals, and residual standard error. So that, it's a good output. It's a lot of the stuff that we would be interested in. Now, just like in the rest of statistics, we want confidence intervals. And so I just pass my model to the intervals function, and it spits out confidence intervals for me. So here we have a confidence interval on the correlation structure. We have a confidence interval for the intercept, confidence interval for that predictor and this predictor. And here even goes far enough to give us residual standard error confidence interval, this is pretty nice. Now we also have an ANOVA structure to work with. And so remember, this is a sequential, like adding of terms, or it's the consideration of using one model over the other. So here we're asking ourselves, should I add that predictor to the intercept model? Should I add this predictor to the sign and intercept model is what the p-value is asking. Now here we're comparing two models, and we can see that adding the var power aspect to the model is not a statistically significant improvement. Now we can ask ourselves, is adding the core comp sim correlation structure to this model, is that a statistically significant improvement? And I would say no, it's not. But I might also look at AIC, BIC, and log likelihood. If I see a big difference, even if it's not statistically significant, I might go with it anyway. Should we go with var power instead of standard weights when we're using this model? Well, yes, we should. This is a pretty big improvement. I can pass multiple models. And one thing that's nice about this is that if I want to use specific contrasts on the coefficients, I can do that very easily by passing a contrast. So inside the ANOVA function, capital L is the vector of contrast, and the position corresponds to the coefficient. Now, we also have the function to extract the residuals, like if I want to do a specialized plot with them. And I can change the type of residual here to be response, standardized, or Pearson, depending on what I'm most comfortable with. And notice that it gives us the estimated standard deviation for us. Now, if I have a more interesting model, these values can change. You notice that the weights are all the same. Since the weights are all the same, we're looking at constant variance assumption applies. The covariance is what is not equal to 0. Now, to be able to work out a lot of these details, what R does, it groups together observations. And this is the get groups, tells me what the groups are. So when you look at these numbers, these are not actually numbers. These are nominal labels. So don't think of these as being addition or inequalities or anything like that. 1 is not greater than 7, and 7 is not greater than 1. These are just labels. And by convention, we do 1, 2, 3, 4, 5 because it's easy. Now there is an ordering to it, and here is like the partial ordering. We can extract the data from our model as long as it's included, and the default settings include the data to be stored on there. we can extract the variance covariance matrix. So if I want to look through and get a better feel of what's going on in terms of that covariance, then this will give it to me. Now you'll notice that if I go down the line with this, this is estimating constant variance, which is not surprising because you notice I made no adjustment to the constant variance assumption on this model. And you'll notice the standard deviations are constant. And if I take the square root of 21.309, I'll get approximately 4.6. And last but not least, we can also make predictions. So if I have a model and I have new data that I want to make a prediction on, I take my model and I set the new data to the new data parameter and I run predict. All right, that's all I got for you. Take care and goodbye.